Alrighty then. So, right, we're back. And back with the PCB making for this SuperCap board. So the idea, if you've not seen the first video, is that we're making some in-house SuperCaps at Loughborough University, part of a research project. Want a nice way of loading them up, putting them under test, a nice little board. Now, specifications for this board are it needs to be very low dropout, so it needs to be able to operate at the lowest voltage possible, so that we can get the most energy out of the SuperCap. We don't want it cutting out at 2 volts. Because if we're using a commercial SuperCap that only goes up to 2.5 volts, then you're only going to get half a volt's worth of energy when you do the maths, and yeah, that's no good. So we want it to drop out as low as possible. So in the previous video, we knocked together this design in Eagle, and just take you through that then. So we got the power in. So this is for recharging the SuperCaps. That's going to be handled externally, so we don't have to watch that. We've got 2 caps in series here. There's 1, there's 2. What's going on there? With just some over voltage protection on them, crude and simple, using a couple of Xenas, and we can turn these on or off, or activate them, should I say, at choice. So if we're using a 2.5 volt SuperCap, we can turn this circuit on, so therefore it will clamp it at 2.5 volts, so we don't overcharge that cap. Or if we're using one of the in-house ones that goes up sort of 6 to 8 volts ish, then we can deactivate that by turning the switch off. Activate this one, and it will clamp it at sort of 6.5 volts there or thereabouts. We got power out, so we can get the power out, which is controlled by a switch, so we can just turn that on or off. That'll go off to some sort of load bank or something like that. It's not an application at this stage of the research. But what we were looking for was a regulator, some sort of buck boost regulator, so that no matter what voltage these are at, whether they're fully charged, so we've got 12 to 16 volts across them, maybe more, or whether these are discharged all the way down to sort of 1 volt across each of them, so therefore 2 volts in series, that we can still get a reasonably stable output voltage, so we can get the energy back out of the caps, and then for the research we can do a load of measurements with that. We're struggling to find a suitable regulator, and to be honest with you, I've not had any luck. I have now emailed Maxim, TI, who immediately replied and said, yeah, we're not going to help you. Brilliant. And Linear Tech have sent me their auto reply saying, yeah, we're looking into this. We'll get back to you in the next couple of days. In the meantime, I found a chip by Maxim, designed for automotive applications, and the thing that caught my eye on this, if we scroll down a bit, bosh, pretty decent data sheet this, quite happy with that. Gone past it, haven't I? That's the graph I'm looking for. Hey. It's on. Oh well. I might have added another different data sheet up. Anyway, it's designed such that it's a boost only in theory, but when the voltage drops too low, it goes into a constant frequency pulse on the boost circuit. So you should still get some sort of power out, but the voltage might be a bit whatever. But that's sort of fine. I can deal with that, I guess. It's a really, really simple chip, very few external components, which is good to see. And yeah, I mean, we've got a Schottky diode there. Might replace that with something clever. You'll see that in a minute. And yeah, and so this is designed for automotive applications where you've got some sort of 12 volt lead acid battery. It goes up to 14 volts when the alternator's on. And when you're cranking the engine, the voltage on the battery will sag quite significantly by, you know, anything. It could be 50% voltage sag down to 6 volts. And this is able to handle that and keep a stable output of 5 volts or 3.3 or 1.8 or whatever we're doing. If you tie the feedback pin to ground, it sets it in 5-volt output mode. And that's what we'll do. I don't really care about the output voltage, what it is. That's the simplest. 5 volts is fine. It's going into a load bank. I don't really care. So let's base, at this early stage at least, ourselves on that particular chip. So the Maxim 608 is not in the Eagle library. I could probably find it and download it. I can't be bothered. So I found the Maxim 634. It's exactly the same package. It's a SOIC 8. So 8-pin surface mount chip. Obviously this is labelled up incorrectly because this is labelled for the 634. So I've basically just put a text dump here with the correct pin out for the 608. So let's sort of wire that in and show you what I'm thinking. I'm going to go off that design note here. So the input goes via an inductor to an external MOSFET. So let's get ourselves a MOSFET, which is under T for transistor. That, and then is there a separate set? No, probably not. N-channel MOSFET. Let's find one in a package that's reasonable. That would be nice. Trench MOSFET, N-channel, 60 volts. Yeah, okay, that'll do for the time being. So let's put that there. We need a Schottky diode, which I'll put in for now, and then we're going to replace it with something clever in a bit that I'll show you. Diode, silicon Schottky. Don't want a tiny package like that because it's a bugger to solder. That's a bugger to etch. Yeah, alright, that'll do. We'll do a through hole. So the Schottky comes off the top of the MOSFET to the output. So off the top of the MOSFET, and then this goes down to the output, which is going to be switched manually on or off. Okay, we need a filter cap on that as well. So we'll go down to RLC, RCL, even resistors, caps and inductors. Go C, it wants to be a polarized apparently, and we'll take sort of 4 or 5 mil thing here. Let's put a 6 mil one on, which will go from there to the 0 volt rail. Okay, that's fine. I'm going to redraw this when the time comes. The bottom of the MOSFET goes to the CS pin, which is pin 8. So this is going to start looking really messy really quickly because we're using a funny thing. And then that gets pulled down with a resistor, ground. So EU, we'll use 805s. I'm more than happy soldering 805s. I can do 603s as well. Where did that go? Weird. So that gets pulled down, ground, 0 volts. We'll fill in the values in a bit. We've got, okay, reference goes to a cap to ground in 5. So add cap, not polarized, cap EU. This will be some sort of ceramic jobby. So again, we'll use 805s on this. Hang on, my eyes have gone completely spaz. There's 085. So there we go. 805 goes from that pin to ground. Right, what's VS? What's pin 6? Pin 6 is A ground, which is right. Okay, yeah, cool. So 5 goes to cat to ground. Feedback, A ground and ground are tied. So 3, 6, and 7 go to ground. 3 and 7, 6. Right, that works quite nicely. So 6 is ground. Oh gosh, that's loud. Oh gosh, that's still loud. Hang on, turn that down. Okay, so they're tied low now. Pin 4, what's that? Shutdown pin. That goes to an on-off signal. That needs to be pulled to be always on. Active low, I think that is. When shutdown is high, enter shutdown mode. So that needs to be pulled down. So full 4 is also tied to ground. Excellent. Let me get my data sheet back up. Right, X goes to the gate of the MOSFET. So that's pin 1. It's going to get horrible now. So that's the gate drive. Out goes to the output, rather unsurprisingly, which is pin 2. That's the sense pin for the output. Crossing wires, arrogant, don't like it. So we need a filter on the input, decoupling cap on the input. Well, considering we're driving this from a cap, that might not be quite so critical. But we will put a placeholder in there and just maybe not use it. And that's going to go there. Decoupled to ground. Let's find an inductor. So we'll go LEU, and for want of anything better, I might just put pretty much a placeholder in here. Honking great big inductor. Comes off the top side of the MOSFET. And then that is our VCC, top end of the cap. That's decoupled. Inductor goes to the MOSFET. That drives in there. There's the Schottky to the output. Okay, so that is that chip done. So let's have a look at what that looks like on the board. Oh, that's the MOSFET. We chose the site package. That's all right. So the chip can come up on here now. MOSFET. Let's rip up that track. Makes sense to have that reasonably close. Inductor, we need that. We need our caps, which are going to need to go close to the chip for decoupling. Let's just drag everything up here so I can see it. Right, Schottky diode is the output diode, which goes straight to the output. So if I rat's nest that, like that somehow. The inductor comes off the back of that. No. might get warm. So I do want to give it a touch of space. Again, we can rejig all this once we've got the rough idea of what's going on. Do that to clean the stilt screen up a little. Okay, so this is our output MOSFET. That can go there somewhere, why not? In fact, actually, it could go something like that. Yeah, that works. The Maxim chip can do something like that, maybe. C1 was our, hang on, I need my schematic up on the screen. C3 is our input cap, so let's put that over there for now. C1 therefore, assuming is the output cap. Yes, it is. So that can actually go down there somewhere. That will decouple down there. Because we do have this decoupling cap. Oh, if that is a decoupling cap. No, that's for the reference voltage decoupling. Well, that should really be as close to the chip as I can get it. That can go there. Input cap fits there quite nicely. And the R1 is the CS. What is CS? What chip select? Excuse me. Forward cap starting up under load. What CS is? Oh, that's a sense resistor. Current sense. Right, so that doesn't want to be an 805 then. It needs to be a current sense resistor. Let me just do this on my other screen. Resistor EU. I want a current shunt. Needs to be pretty big. Where shunt resistors are. Let's pull this over. Not under shunt. Under current? No. Not under air, is it? Well, we could use a MILF. Never soldered one of them before. I know they're quite popular for shunts. Interesting. Oh, phone's going. Right in a bit. Resistor. Resistor shunt. Here we are. What a one. Something like that would be probably more likely that. Okay, so I'm going to replace that resistor. Okay. Oh, there we go. Right. Okay. So there's our sense resistor, which goes to ground, because that comes off the back of the inductor. So that really needs to be quite close to that inductor. There looks as good as any. No, it doesn't. No, that comes off the back of the MOSFET, comes from the inductor. Ah, so yeah, that can sit there then. Keeps things nice and tight. And then the Maxim chip. Have a look at how we're going to wire this. That look cool. Let's start getting some wires on it now. I can go up to there like that. These get tied together. Do they? N6. Oh, because that's the MOSFET. Sorry, I'm thinking that's the chip. Come on, switch on. And then that's the sense to the chip. So this wants to go directly to there. So we're sensing that as best we possibly can. And then the output of the MOSFET can drive straight up like that. Not really. Can get away with a higher current path. We're going to change the width of these things. Not sit well with me. Cap goes straight in. Cap goes straight in. Through the inductor into the MOSFET. Where's the path? Oh yeah, because that's your path there. And then that's your boost, which is this little loop, ground through the MOSFET. Looks upside down. Not ignoring the inductor. Oh no, because that then shorts the inductor to ground, which gets you your current spike. Yes, okay, that's correct. N14, what's that? Let's do a show on that wire. That's the gate drive. Okay, so that one don't care about too much. 50, let's take that down to 20. That can come out something like that. That's going to make it a bit to solder, so I'll tidy that up in a bit. This is our output sense. This is now going to be quite a long track, which I'm not overly keen on. Yeah. Well, let's put it in for the time being. Decoupling for the reference voltage needs to go nice and close to the chip. It is there. Okay, so that gives us a reasonable boost circuit. So that's not great because that's huge capacitance and inductance, but we, as I say, we're going to tidy this up. So this should, in theory now, give us a stable-ish 5 volts out. Reasonably clean. Yeah, I'm reasonably happy with that. Obviously, we're going to shrink this board down as well. Now, it would be nice to have some sort of output identifier So what we need is an R resistor in an 0805. Where do I want this? I want one there, and then an LED. LED, LED, and LED. We'll go with a 5mm LED. Massive, why not? And one of those gets tied to there, one of those gets there, both tied together. Right. I appreciate it's on my screen. Eagles bobble. So the idea here of that there and that there. These track sizes are, yeah, I'm going to sort these. That can go to there, there. Okay, so the idea here then is that I just move this tilt screenage like that. Then to some text. DC on. We'll put that on the top silk screen. I'll do if I can find it. Where's it gone? What? There used to be a T silk. What's going on there then? So that one is DC on, and this one is out on, output on. So this, if this LED is lit, then we know the DC converter is outputting a voltage high enough to drive this LED. And then if this switch is supplied, so therefore this terminal block is live, then that will also illuminate to tell us that this output connector is live. Now we could, excuse me, put another one in. I think we probably will. Make it look like Blackpool Illuminations. And go clickety click. Do this on the other screen. Like that. And then we can have a third LED facing reasonably similar. Smash, move. That can go there. Like that. And then we're going to do copy, paste, and this is SC charged. So that light is tied directly to the supercap input. Supercap input here. So if there is a charge across here, then we will get this light illuminate. Now, to limit current through this shunt, we could put some LEDs in here in series with the diodes. Tell us that one of these shunt circuits is active, but I'm not going to do that because it's not binary switching, so they might not light up bright enough. I am going to do though, change this back to 50 mil. In fact, turn the grid on. This can come over here. Right, so let's just do that again. Rip that up. That can actually tie straight into there. Oh, wrong button. There we are. So this is looking more reasonable. What we can do is select all, move, something like that. Got no dodgy floating grounds, have we? No, that's tied. That's tied. That's a good path round there. That's okay. Oh, I need to sort these connectors out. Give me a tick while I do them. They do actually have more than one connecting point. Good. Now I can tie that up there, tie that up there. That to that one, that to that one, that to that one. Good. Okay. Grain planes are that can get back round there. Design rules. I'm going to load wrong one. I want my Dropbox. I want my Eagle folder. And I want the SparkFun design rules. Check one width. Yeah, no, don't care about that. That's just grain plane fill. Excellent. So that, in theory, should now work. We've got a bit of protection on there as well. What do we think? Is that going to work as intended? I don't know. What else do we need on the board? Ooh, new tab. Will this show us what it'll look like? Oh man, mental. Go on, initialize in preview. Oh, this will be mega if it does. Whatever it is, it's not quick. Come on, crunch the numbers. Oh, blimey, yeah, it's not quick, is it? Do I really care that much? It'd be nice to see. Well, I'll let that chug away. We can obviously shrink the vertical height of this down a bit. We'll do that group first. Oh, yeah, something's gone. Oh no. And then that group. Like that. Oh, look at that. That's cool. And then we can pull that back into there. And then we can rat's nest it. That's really cool. I like that. Didn't know you could do that. That's really wicked. So we can see on here what it's going to look like with all the solder masks, silk screens, and stuff like that. Oh, and I can see, yeah, talking of silk screen. And down there, a bit more sensible. Weirdo, there's only a tiny gap there, but quite a big gap here. Quite odd. Yeah. I'm quite happy with this current sense. Yeah, that's quite short. That's a direct path. Yeah, no, it's okay. It's all right. So I said we were going to do something funky with this output diode. Right, we are. Now, can I do it? I'm in here. The linear device. Hang on, let me just find the part number. Linear technology. Which is of course now analog. Getting that. Products, power management. Power control. Not under there. Not what I want, that's it. This is what I want. Ideal diodes. These are really cool. Ideal diode controller. So, okay, so V and min needs to be really quite low. Joule, don't need it to be a joule, but yeah, no, I don't want a massive package like that. Load switch current capability 500 milliamp. No, that's not going to be enough. Too big a package. Doesn't necessarily need to be monolithic. They do one that's just like only a couple of components. 4415, that sounds familiar. Not too many external components for what it needs to be. External P channel, no, it doesn't big. Find the right one. God, it's a 3-phase. Aha! That's what I want. Thin sot. Thin sot. S5 package. Ooh, super plastic. I need one that I've got a package for in Eagle. Hang on, let's see what. P channel. External. I've selected P channel external, and an external AND channel comes up. So that's not an AND then, that's an OR. Let's just do P channel. Pretty sure it's the 4415 or 1. No, it's not. I'm chatting rubbish, man. Need V and min to be pretty low. Who's this? So many really good quiescent current. Oh, I can't do any of that. 4418. So many external components because it's a dual power path controller. Alright, let's go single. Are there any thin sots in Eagle? Not what I want. I'm in thin stock. Oh, that's better. MS8. MS8. Oh, MSOP. Is that what it is? Yeah, it could be an MSOP. What was the... Oh, V and min 3 volts. Oh, someone at the door. Bear me a sec. Right, sorry, I'm back, troops. I'm back. One of my neighbours, apparently Amazon delivered something 3 weeks ago and didn't tell me they'd delivered it. And sent me another one. Right, where were we? 4352. That's probably looking promising. It's QFP. Not the end of the world being QFP. Oh, it does come in an MSOP 12. Right, that'll do. Let's stick that onto the screen. MS12. Stop 12. MSOP 10. I'm just looking for anything that's an MSOP 12 now. 12, 1, 2, 3, no, that's too many. Connectors. No, no, no. Pulse. Flipping out, there's some crazy isolation there. These coilcraft lint. Not what I need here. An MSOP, come on. MSOP 8. MSOP 8. MSOP 12, that'll do. Does it have the pad? Documentation and its data sheet. Doesn't have a pad, but that's not the end of the world. Right, well, screw it. Let's just use that. Okay. In fact, no, I do want that. So I want fly. VCC int is going to be labeled there. Yes. And then VDD, I'm going to call it, for anything better, is going to be that one. So, you can delete out the diode. Now, V in is pin 1. Right, hang on. Look at the design notes here. I need to get the right that as well. Going to be pointing in the way, so it's going to have to be E, right? That should have low resistance. Source V in a type together. And it can use an N channel. Excellent. So we can use the same N channel MOSFET that we're using here. Over there for the moment. So V in and source get tied together, which is pins 12 and 1. V in the diode. V out goes off to the load, which is pin 8. Yep. Ground is pin 9. 0 volts, pin 9. Yeah. So the rest needs to be tied to anything. 0V, so pin 4 is to ground as well. Lazy. UV, VCC get tied together. 2 and 3. Which are just decoupled to ground. Source is decoupled to CPO. So that is 12 being decoupled to 10. Naughty, and put that upside down. Gate is pin 11. Take that there. Pin 11, this is so messy. That goes to there. Power in is V int, which is that side of the MOSFET, and that's V out. That side of the MOSFET. So that is an ideal diode, okay? So what it's doing, in fact, tell you what, let's put it on the circuit board first. Clear that out, where I should have left space. Do. That's our output MOSFET. And sit up there for the moment. This is our ideal diode controller. There's the gate. Gate's pin 2. Sensible. That looks sensible. That looks sensible. So just a couple of decoupling caps. Okay. Caps in. Nice and close. And then immediately ladder. Let's smash these. Smash, smash. IC2. And that's C5. Where's the movie thing? Or did I not smash that? Smash. Smash, 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 smash. No, no. Oh, it's there. Okay. Tidies that up a touch. Don't need wrong anyway. So if we now start filling this in a bit. Like something. And on the RAM, these tracks are too big. 15 will do it. Don't like at all. Moment. That's no, it won't do for the moment. That's bug me. Come out straight and then go in. Goes on that. Can come in there like that. This can come around the outside. Decoupling cap, isn't it? So that's okay. Go in there like that. That's a decoupling cap. So we want them straight in like that. This is going to come there. That's going to bugger to folder. I need to get rid of that exposed pad. This can now be a high current path. 20 for now, which is particularly high current. I have to admit. Click, click, click. And then I guess it can go straight off there, off the edge. So that's now, okay, a few more components than a Schottky, but the resistance, the on-state resistance of a FET is considerably less than a Schottky. So the losses across it will be much, much greater. Much, much lower. More reduced. The word I'm looking for. And of course, if you choose a decent MOSFET, it's, you know, you can get really, really good sort of sub 10 milliohm drop across there. Miles better than a Schottky. Ready yet? And the way the power path controller works is, say the MOSFET is off. If you've got a forward voltage, so your voltage on your input is higher than the voltage on the output, it goes, okay, current's going to flow in the direction you want it to, so let's turn the MOSFET on. It's going to go through anyway through the body diode. It turns the MOSFET on, which brings that resistance right down. If the current reverses, the voltage reverses, so it's higher on the output than it is the input, then it turns the gate off. Body diode is reverse bias, so it doesn't conduct either. So you've got blocking in the reverse direction. So it works, you know, just as well. And as long as this is switching and the comparator's quick enough in here, then it's as quick as any Schottky, really. Certainly, speeds we're looking at, we're not doing anything kilohertz, but they will do kilohertz. So it's a pretty much drop-in replacement. I don't like this track there. That's horrible, isn't it? A better way of doing it, though. Don't really care that much. Okay. So that is our shiny little board. We can get rid of that diode now. We don't need it. So that can go. I can tidy this up, but in general, I'm quite happy with this. Interested to see your comments. Anything you can think of that may improve this, and yeah, I mean, I'm going to tidy it up, but in general, that's it done. Hope you found it enjoyable, and I'll see you next time.